tectonics. So this is going to tie together our two earlier ideas of continental drift and seafloor spreading together into one geologic theory. So let's get started. First off, our theory of plate tectonics states that the pieces of the Earth's lithosphere, so the Earth's lithosphere is broken up into different pieces called plates, that these plates are in slow, constant motion driven by convection currents in the mantle. And so we saw in our seafloor spreading lab yesterday, right, that convection, when the material moves up like it did in the jar yesterday, when it reaches the top of a layer, it moves out to the sides. And so that sideways motion of the convection currents in the mantle is going to pull or push the lithosphere that's on top of that convection current along with it. And so if we were to drain out all the oceans and get all the water on Earth to go away, we would see that the Earth's surface is broken up into a bunch of different plates. Right? There are about 15 major plates. You do not have to memorize them, but this is their distribution across the world. You've got the big ones are the North American, South American, African, Eurasian, Indo-Australian plates, and the Pacific plate. Notice that there's no Atlantic plate. Right? The Atlantic Ocean is totally covering up just pieces of other plates. And where these plates meet, we call that a plate boundary. And there are a couple different types of plate boundaries that we're going to talk about right now. So, how do the Earth's plates move? The convection currents in the mantle are the major force that cause the movement of these tectonic plates. So, as the convection current reaches the surface, it moves off to the side and drags the plate with it. And so, at these plate boundaries, they can move in many different ways. Plates can collide, they can pull apart, or they can slide past each other. And each one is a different type of plate boundary. So let's get started with the first. We've got our divergent plate boundary. And a divergent boundary occurs when two plates are moving apart from each other, right? To diverge means to move apart. If this occurs with two oceanic plates, you would get seafloor spreading, right? And this is what we see in the middle of the Atlantic Ocean at the Mid-Atlantic Ridge. You've got two oceanic plates moving apart from each other. We've got oceanic crust on one side, oceanic crust on the other side. New crust forms in the middle, and we create a wider and wider and wider ocean. If it's on land, you actually get a deep valley forming, and this is called a rift valley, right? In Africa, in East Africa, there's a giant rift valley as the African plate is starting to split itself apart. And so as these sides of the valley move apart from each other, the valley floor falls down farther and farther. Eventually it will fall down so far that it will fill with water and become a new ocean. At that point you'd start to get seafloor spreading in the middle. Next up is our convergent boundary. Right? To converge means to come together. And convergent boundaries cause collisions. So this is a collision between two different plates. And depending on what types of plates are colliding, we're going to get different results. So first is if we have two oceanic plates collide. So this is oceanic crust colliding into oceanic crust. When two oceanic plates meet, one of those plates is going to be slightly denser than the other, and it's going to subduct under the less dense plate, forming a trench. Right? Notice the water isn't going anywhere. The water is still just on top. This is the actual sea floor itself is getting pushed under the other side. As it goes down, that plate can melt, and the magma that forms will bubble up and form volcanic islands. This is how, and so this map is showing a little bit of Alaska, right? These are the Aleutian Islands. This is part of Russia, and then over here are the islands of Japan. Notice there's a really deep trench offshore of all of these, where the Pacific plate is getting pushed under either the North American or the Eurasian plate. Right? And as that plate, the Pacific plate gets pushed down and melts, it bubbled up to form all of these islands. Next up, we have a continental and oceanic plate meeting. So if an oceanic plate comes into a continental plate, the oceanic plate always loses. You're never going to have oceanic seafloor ride up and over a continent. The oceanic crust gets pushed under, and again that's going to melt and bubble up, but instead of forming volcanic islands, we're just going to get volcanoes forming on land. Right? And so this satellite picture shows this is Washington State up here, Seattle's right around there. and you've got this small plate offshore. It's called the Juan de Fuca plate. It's a remnants of an earlier plate that has been mostly destroyed under the U.S. But this plate is getting subducted under the North American plate, and you've got the Cascade volcanoes right here. Volcanoes like Mount St. Helens, Mount Adams, Mount Rainier, and a couple other volcanoes all the way down into California. And so that's where those volcanoes come from. Lastly, we have two continental plates colliding. So if two continental plates collide, they both have very low density, so neither one is really going to sink. Instead, they're going to collide and smush together and form big folded mountain ranges. So these mountains are basically made of huge folds of rock. And we see this in the Himalayas in India. Right? India used to be its own subcontinent, but a couple million years ago, mass started pushing its way into the bottom of Asia, forming these huge mountain chains along that collision boundary. Our last type of boundary is called a transform boundary. And at a transform boundary, the plates are sliding past each other. Right? And this creates a lot of friction. Right? These are huge pieces of rock. They don't really slide very easily. So rather than just glide past each other, they tend to move in very jerky steps. Pressure will build, and all of a sudden the plate will shift a couple centimeters. That shift releases a bunch of energy, which we feel as an earthquake. And so one of the most famous transform boundaries in the world is the San Andreas Fault in California. LA is right around here. San Francisco is right here, right on top of the fault. This little piece of North America is actually on the Pacific plate moving northwest, while the rest of the North American plate is moving to the southeast. So you get a lot of earthquakes as they slide. And just a couple pictures of a transform boundary in action. Right, this is an orchard of trees. These trees were all planted in straight rows, but because the fault moved along that transform boundary, one plate moved one way, one plate moved the other, they're no longer planted in straight rows. And this fence is actually at a park north of San Francisco. It used to be one continuous fence, and over the last about the last 100 years, you can see that it's clearly shifted in position. Right? Part of the fence has shifted one way, part of the fence has shifted the other way as those plates move past each other. That was all for your notes for tonight. It was a little long, but a lot of good information there. Make sure you write down 3 questions, and we will go over that in class on Monday. See you then.